In this video, we're going to talk about section 2.2, which is determining volumes by slicing. We have three main methods today. We have the slicing method, the desk, and washer method. So in the previous video, we saw how definite integral plays a huge role in finding areas between certain curves. In this section, we'll see how definite integrals could also help us to find the volumes of certain shapes. Now, in general, we know that the volume is length, width, height for certain solids. And we know certain formulas for like a sphere, a cone, and whatever. But what if we have an unknown shape and I want to find the volume of that shape? The definite integral plays a huge role in calculating that volume. So let's see how we're going to calculate volumes. Before we calculate volumes, let's define what a cross-section means. So a cross-section of a solid is if you take a solid and you intersect it with a plane. Once you intersect it with a plane, that intersection is called a cross-section. Now, a cylinder is any solid that we can generate by taking a region along a perpendicular line to that region. Okay, so let's look at this graph here. If I have this cylinder and I take a plane and I intersect it with it, once you intersect it, you're gonna get this semicircle. So this is what we call a cross section. So if we want to evaluate the volume of this shape, the volume would be just the area of this cross section multiplied by the height. So this is how we get the volume. Now this works here because if you take this plane and intersect it at any point along this cylinder, we're going to get the same cross section. What happens if I intersect the shape with the plane, but I get different kind of cross sections? So in this case, we're going to use the definite integral to calculate the volume of the solid. So how would we do that? We have three steps. I'm going to slice my solid into pieces. I'll calculate the volume for each piece separately, and then just add all of the volumes together, and that would estimate the volume for the whole solid. So let's look at this shape here. So if you see, if I do a plane here, I'm going to get this cross section. But if we take the plane to be here, I'm going to get something similar, but with different shape. It's going to be bigger, right? So here, I can't just find the area of the cross section and just multiply it by the height. Because if you take the area for different cross sections along this solid, you're going to get different areas. So let's see what we're going to do. We're going to take this solid S and we're going to divide it or slice it along the x-axis. So we're going to slice it that way to create different smaller solids. My A of x would represent the area for the cross section at each point x. So the area for this, then the area of that, then the area of this, and so on. And here we're taking a regular partition, which means the distance between each point is going to be equal. And now S of I is the slice of S stretching from xi minus 1 to xi. So it's each part here. So S1, S2, S3, and so on. And xi star is just an arbitrary point in each of these slices. Okay, so the volume for each slice. So for example, if I want to find the volume of S3 here, I'm just going to find the area of the cross section and multiply it by the height, which is just delta x, right? So the volume for each SI is just the area multiplied by delta x. But to approximate the volume for the whole solid, I'm just going to sum each volume of these SIs. So we're going to have this formula here. And now this is a Riemann sum. So we know if I want to find the exact value, I'll just take the limit. But taking a limit for a Riemann sum just creates a definite integral, which means that the volume of a solid with a non-constant cross section is just the area, it's just the integral from a to b for the area of the cross section. So this whole method is called the slicing method. I'll just slice my solid, find the area, the volume for each slice separately, and then just sum all of these volumes. But this whole technique is just doing a definite integral. So it's quite easy. I just need to find my a of x and just integrate it. So let's look at the strategy here. We're going to look at the solid. We're going to define the cross section, and then we're going to find the formula of the area of that cross section and then just integrate. So it doesn't make sense, right? It's a bunch of techniques, bunch of methods that don't make a lot of sense right now. So let's look at the first example to understand it better. We want to use the slicing method to derive the formula of the volume of a circular cone. So the first step, always, you need to graph. If you don't have a graph it to understand exactly what we want to do. So here, if I graph a cone with a circular base, I'm going to get this, right? If you take a cross section here, you're going to have a circle with radius r, for example. But if you take a cross section here, you're going to have another circle, but with a different radius. So that's why I can't just take the area of this circle and just multiply it by the height, because at each part, I'm going to have a different radius. So this whole thing has height h, let's say, and for each cross section that I take along a certain value x, I'm going to have a distance x. Okay, so we know that our cross section is just a circle with radius r, but this r is not constant. It changes with the different slice that I'm taking. So I want to create a formula that relates this r with the r that we already know the exact value of, which is just r small. So to relate them, we can notice that r capital and normal R is in a right angle triangle here. So this is R, this is R, this is distance x, this is distance h. And I know that these, like the big triangle here and the smaller triangle here, they're similar triangles. So if they're similar triangles, they have ratios that could be helpful here. So if I take R over h, this is going to be equal to R over x. Then if you cross multiply, your R is just going to be Rx over h. So going back to the cross section, we said the first thing is we identify the cross section, then we find the area of that cross section. But since this is a circle, the area is just pi r squared. But we already said that r is equal to this. So if you substitute, you're going to get this. We identified the cross section, we found the area. Now to find the volume, we just take the integral. So this is going to be from 0 up to h. So from 0 to h, and just take this pi r squared x squared over h squared dx, and we can just evaluate it normally by taking the antiderivative. plugging upper bound minus lower bound would give me this. And once you simplify, you're going to get the formula of the volume of a circular cone. That's it. So it's all about graphing, finding the cross-section, finding the area, and just finding the volume directly using the definite integral. Okay, so this is for the slicing method in general. Let's look at something that's called a solid of revolution. If we have a certain region and we revolve it around a certain line in the plane, we're going to create a solid. That solid is called a solid of revolution. So let's look. If I have this region in the xy plane and I'm going to revolve it around the x-axis, so if you take this region and just rotate it around the x-axis, this is going to create a solid. And this solid is called a solid of revolution. So let's see why this is helpful. We want to use, in this example, the slicing method for a solid of revolution formed by revolving the region between f of x is 1 over x and the x-axis over the interval 1 to 2, and we want to revolve it around the x-axis. So you have a question like this. The first thing, you want to graph. I'm going to graph my function 1 over x, which looks like this, on the interval given from 1 to 2. And we have the region between the graph and the x-axis, so that's going to be the region that we want. Once you take this region, let's look which line do I want to revolve this region about. We want to revolve it around the x-axis. So you just rotate this whole thing around the x-axis, creating this solid. Once you got the solid, you can apply the slicing method directly. You want to identify the cross-section and then just evaluating the definite integral to find the volume. So the cross-section here, as you can notice, is just a circle. And this circle has radius f of x, right? Because this distance from the center of the circle up to the end of the circle is just this point here. But this is my y when we're given a certain x, which is just f of x. Which means that the area for the cross-section would be just pi my f of x squared. Because the area of a circle is just pi r squared, and here r would be f of x. Okay, but what is f of x? It's just 1 over x, and we were going to square it. If I'm taking the volume, I need to integrate on this interval given, taking the area of the cross-section. So this is finding it directly by the antiderivative. Upper minus lower. Which is just pi over 2. Okay, so the slicing method is not too bad. You just want to identify the cross-section, find the area, and integrate. The desk method is kind of a special case of the slicing method. We're taking the slicing method with solids of revolution. That's the disk method. The only difference is with the disk method, we know for sure that the cross-sectional area is just an area of a circle, because you're going to integrate it around, revolve it around the x-axis or the y-axis, or whichever line. But if you do that, if you revolve it around a certain line, it's always going to create a circle. So that's why we know that the cross-section is just a circle. So let's look here. If I have this graph, if you take a thin rectangle under the curve and then you revolve it around the x-axis, this is going to create just a circle. So the cross section here is just a circle. And I can find the area easily, pi r squared. How about if we take the area under the whole curve here? So you have this region, and you want to revolve it around the x-axis. You're going to create this solid. But this solid, no matter what point you choose, if you take the cross section, this is always going to be a circle. So the area of this circle is just pi. The area for any of these cross sections is just pi r squared. But r squared here, r is always going to be f of x squared. So if we want to generalize, a rule for the disk method, it's always having a function f that's continuous and non-negative, and we have a region R, which is always bounded by your function f, and below by the x-axis, you have an interval AB. The volume for this solid, revolving from taking R around the x-axis, is always going to be integrating pi f squared, because the cross-section here is a circle, which has an area of pi r squared, and r here is just f of x. So it's quite easy. For example, if I have this function here, and I know that I have the region between this function and the x-axis over this interval, and we want to revolve it around the x-axis. So you always start by graphing. So you have this function. Since I want it from 0 to 4, this is going to be my region. You want to revolve it around the x-axis, so you're going to create this solid of revolution. And if you can see, whichever x value you take, you're going to have a circle as a cross section, and since we're using the disk method, your volume is always the integral from a to b, pi f of x squared d of x. So this is just from 0 to 4, pi your function squared d of x. So you can find it easily. Upper minus lower, and you find your answer. If you want to apply the slicing method, you have this cross section, and since it's a circle, this is just pi, and your r here is just f of x, and then you integrate, so you're going to get the same exact formula. Okay, now what if our solid of revolution was generated by revolving around the y-axis instead of my x? We're going to follow the same exact technique, but instead of integrating in terms of x, we're going to integrate in terms of y. So we're going to have this formula. So let's look at this example. If I have a region bounded by my function g of y and the y-axis on the interval from 0 to 4, and I'm going to apply the disk method with the revolution around the y-axis. Same exact method. You graph your function, you're going to get this, and then from 0 up to 4, so this is your region. Then we're revolving around the y-axis here. So you're going to have this solid of revolution. This solid of revolution, since we're using the disk method, we're going to have a cross section of a circle. But since it's a circle, I'm going to have the area to be just pi g of y squared here. And using the disk method, I know this is just pi g of y squared d of y. My g of y is just 4 minus y squared d of y. And we're going to have the same exact thing as we had in the above example, and so on. Okay, so far our solids are filled. I don't have any holes, I don't have any cavities, I don't have anything. So I can just apply the formula directly. But what if I have a solid with a cavity inside? I have some kind of hole inside. Whether it was like evaluating with an axis of a revolution other than the x and y axis, or if I have a region of revolution created by two graphs or two functions. So when we have these cases, most of the time we're gonna have like a cavity between these two functions, so it's gonna create like a hole inside of my solid. So when the solid of revolution has a cavity in the middle, the slices used to approximate the areas are not going to be discs. We're going to have something called a washer. So a washer is just a disc with a hole in the center. So when you have that case, this is where the washer method comes in place. So let's look at this example. If I have these two functions, and let's take this small rectangle. If I want to revolve it around the x-axis, as you can see, we're going to have a hole right here because we have nothing here. Once you revolve this around the x-axis, it's going to create a hole here, but this whole thing around it, it's going to be filled. So that's why we get this solid right here. So now what if we take a big region between these two curves? Once you revolve it around the x-axis, we're going to have this solid, but this solid has a cavity inside. So this whole thing, this like kind of cylinder kind of thing, this is empty. And everything around it is solid. So if I want to find the volume for that solid, I need to apply a different method. So how about we look at the cross section here? If you take a cross section of one of these, you're going to have kind of two circles where this is the only filled part. And this thing here, this is empty. So to find the area of this, obviously, I'll take the area of the bigger circle, then subtract the area of the smaller circle, and I'm going to get the area in between. So this is exactly what we did here. If I want to find the area, I'll take the area of the big circle, which is the area when we have f of x as my radius, and then I'm going to subtract the area of the smaller circle, which is taking g to be my radius. Once you subtract, you're going to get this, and then the volume for this solid is just integrating the area, so we just take the area of the cross section. Okay, so let's look at the main rule for the washer method. If I have two continuous function f and g, one of these functions is bigger than the other, and I have a region R bounded by these functions. So f above, g below, and the lines x and a to the left and right. To find the solid of revolution revolving around the x-axis, we just take pi fx squared minus x squared, and we integrate it. So this is the area of the cross section. This is the area of the bigger circle. Then we subtract the area of the smaller circle to get the area in between, which is what we want. So let's look at this example. If I want to find the solid of revolution between these two curves on the interval 1 to 3 around the x-axis. If you graph it, you're going to get these two functions. And if you revolve it around the x-axis, like that. So if anything here, this is going to be empty. Because the region that we're taking is this region in red. This is my region that I started with. But once you revolve it, you're going to get everything around this area. This is filled, but this region in green, this is empty because I don't have anything. I don't have a region below the graph of G. So if you take a cross section of this, you're going to get a circle, but I have a smaller circle where this is empty. I have a cavity here. And to find the area of this shape, I need to take the area of the bigger circle and then subtract the area of the smaller circle. But if you look, this circle right here, it has radius f because this distance, I have a point on my function f. So the area of the bigger circle is just pi f squared. And the area of the smaller circle here, this has radius g because once you hit it, like if you take a smaller circle here, for example, once you hit the graph, you're going to get the graph of g. So the radius is g and the area is just pi g squared. So the area in general is just pi f squared minus g squared. So this is pi this squared minus 1 over x squared. Once you simplify, you have pi x minus 2. And we know that the volume is just the integral from a to b, pi f squared minus g squared. So you just take this and you plug it there. From 1 to 3, pi x minus x to the minus 2 dx, and you calculate it normally. Now similarly, if I want to do the washer method applied with the revolution around the y-axis, same exact process, but we're integrating in terms of y. Now I want to look at this question here. What if we're revolving around a line different than the x or y axis? What if I want to revolve it around y equals -1? So let's read the question. I want to find the volume of solid revolution bounded above by x plus 2, bounded below by the x-axis from 0 to 3 around the line y equals -1. So this is my function x plus 2. This is my x-axis, and from 0 to 3, we're having this part to be my region. And we want to revolve it around y equals -1. So this whole thing, we're revolving it around the line. Oops. So here, since this area is empty, once you revolve it, we're going to have a cavity inside. So once you revolve it here, this whole area, this there's like a cavity, a hole inside of this solid. Anything outside of it is filled. This is the volume that I want to calculate. But anything inside is just a hole. So if you take a cross section, you're going to get this. But here, the only thing different, if you want to take we want to find the radius, it's not going to be directly our function. Because here, let's look. This is the big circle. This is my center. And if I want to take the radius, I'm going to take it up to the end of the circle. So yes, it did cross my function x plus 2. But x plus 2 is only x plus 2 from the x-axis up to x plus 2. So this distance is x plus 2. But I have an extra distance here, which is 1, right? Because we always take distances in positive. So the distance for the whole radius for the big circle is going to be x plus 2 plus 1. So that's why the radius for the big circle here is x plus 2 plus 1. How about the small circle? If I take a cross section here for the small circle, because this is the small circle is always the cavity, the hole. So this is the circle. If you take the radius from the center up to the end of the circle, this distance here is 1, right? From 0 to -1 is just 1. So the radius for the small circle is just 1. So if I want to find the area for this whole region S, it's going to be the big circle minus the small circle, so it's just pi big circle, which is x plus 2 plus 1 squared, minus the radius for the small circle, which is just 1 squared. And if we want to evaluate the volume, we're going to take the integral from 0 to 3 of the area. In terms of x. Once you simplify, you can integrate and find the value directly. So here we're applying the washer method since we have an empty hole or like a cavity in my solid of revolution. So these are like the main ideas of this section. It's all about the slicing method and then applying special cases with the desk method or the washer method depending on the question. So it's all about practicing and finding a technique of which method is better. In the next section, we're going to learn another method that could help us evaluate the volume. And then I'll compare all of these methods to show you the cases where each method is used. If you have any questions, please email me. If you need extra office hours, just email and we can find a time that works for both of us. These are some suggested problems from section 2.2 if you want extra practice. And then if you go to Lumen homework number 2, you can do the problems from 6 to 10. Good luck with everything, and I hope this week ends well for you.